Alright guys, so we're going to explore the idea of creating electricity on a large scale. And we haven't really talked about nuclear energy yet, but we've talked a little bit about fossil fuels and our dependence on them. But over half of the electrical power generation in the world comes from nuclear power or coal. So nuclear and coal-based power plants together make up half of the world's power. And how do they do that? They do that through this incredible feat of engineering called the steam turbine generator. The steam turbine generator is so efficient and so effective that more than 100 years after its invention, it's still what's being used in modern power plants. So that's why we're going to focus on it today. All right, so we're going to draw a really basic version of the steam turbine generator. And we're going to start with a fuel source. We're going to call this thermal heat or thermal energy, and it's whatever it is that we are going to be burning in order to generate heat. Okay, so I'm gonna add flames here. This could be nuclear power, which obviously wouldn't have flames. This could be burning peat moss or wood or coal or fossil fuels, whatever it is. That is what we're gonna say is our heat source. All right, above our heat source, we're gonna add what's called a boiler. And I'm just kind of representing this as like a box with grates. Because this is where water is going to be boiled from our heat source. Now this boiling water is what is going to provide the kinetic energy that we need to spin a series of turbine blades. All right, so here's my turbine blade that I'm going to represent with just a series of circles. They're going to increase in size as I move up the pipe here of my steam turbine generator. And, you know, in real life, this would be a massive, massive structure where, I mean, the size of a room, where the blades themselves are increasing in size and they're changing in shape as you increase and move through. The physics of it is actually very complicated, and I'll post a video about them actually if you are interested in the physics of it. So the steam is what's going to spin this turbine, and the turbine is now attached to a shaft. So these turbine blades are working on a really basic principle that by spinning these wheels connected to this shaft, I can convert thermal energy into mechanical energy. So there's movement here. So this shaft is going to move where I drew my arrow there. And amazingly enough, this shaft is connected to a copper wire inside a magnetic field. And we learned in our last lab that this is what creates electricity. So this is electrical generation. So now we're moving from kinetic energy to mechanical energy to electrical energy. So you can imagine if you're doing this on a large scale and you have turbine blades the size of a room and you have a massive generator, which is copper wire inside a magnetic field, you can have electrical generation. All right, so we're not done with our design yet. We actually need to collect some of that water that has been moved along the turbine blades as steam. It would be really inefficient to just let it, I don't know, flood out onto the floor. So it's connected to this condenser here, collects all of the excess steam, and this water can then be flowed back into the boiler. Okay, so this is my super, super simple basic design of a steam turbine generator. Now, a couple other things that I didn't quite get to detail out here. From the boiler, you can see that steam moves along the pipe. There's my steam, and actually is what is creating the turbines to spin. All right. Now, in my actual boiler, there is an exhaust pipe for the pollution from my thermal energy source. Okay, so this is my heat, my thermal energy source, my boiler, my exhaust pipe, which is where all of the carbon dioxide and methane and all sulfur from burning my coal or whatever it is goes into the atmosphere. I have my steam turbine that is spinning from the kinetic energy of the boiling water. I have my generator itself, which is just the very simple copper wire inside a magnetic field. And then I have my condenser that collects the excess water and moves it back into the boiler. Now, in a nuclear power plant, you actually would have another piece to this. We're going to do nuclear power design as well. Don't worry, we'll get there. I know some of you guys are excited about it. But there would also be a cooling tower, which releases steam. All right, so let's outline these. We have our heat source. This is a burned organic fuel, nuclear chain reaction, geothermal heat source, whatever it is providing thermal energy. We have our boiler, where water is boiled into high pressure steam. We have our exhaust pipe, which is the byproducts of burned fuel that has to be released. It has to go somewhere into the atmosphere. We have our steam turbine, where pressurized steam turns these blades. We have our generator, which is connected to the turbine by a rotating shaft. When the turbine spins, the generator is spun to generate electricity. And we have our condenser, where steam is cooled, becomes liquid, and can be sent back to the boiler to be released. Okay? So this is the basic design that I need you to know.